I am Matt Butcher. I'm the CEO of Fermyon Technologies. You asked this morning, Steve, who was there before 1.10? We were really, really early. We were in 1.1. Was when we started working on Kubernetes. We were at a little startup called Deis, and we were building a PaaS that was intended to compete with Heroku, who was sort of the dominant PaaS provider at the time. And kind of the secret sauce that we were going to bring to this was we were going to use containers to do this, but we didn't have a really good container orchestration system, so we were auditing all of these different container orchestrators like CoreOS Fleet and Apache Mesos and Docker Swarm, and along comes this impossible to pronounce orchestration system out of Kubernetes, out of Google, called Kubernetes, and we started playing with it, and I just really liked it. It really resonated well with the way that I had thought we should be able to do things. I'd worked at Google previously and seen Borg and was like, oh, this is like all the magic of Borg, but actually simple. And simple it was at the time. It has since gotten less simple. So we kind of re-platformed onto Kubernetes. And then in the process of this, started looking at different gaps in the Kubernetes ecosystem. One of them was there was no package manager. And so we started building a package manager. The original name of this package manager was Kate's Place, and it was all coffee shop themed. And we did this as a hackathon project inside of Deis. So we won the hackathon, the internal hackathon. I've got a $75 gift certificate for Amazon that the three of us who worked on it split. I spent my $25 on coffee. And the day after we did this, the CTO and CEO called me and said, and whenever the CTO and CEO both call you, it's like, I'm getting fired. I know I'm getting fired. And they're like, so that Kate's Place thing, we liked the idea. We think that maybe there is room in Kubernetes for a package manager. You should do it. We'll free up your time, give you a team, go build this thing. There's just one caveat. You cannot have a coffee shop named coffee shop themed package manager. So Jack, my co-creator, and I sat there going through a nautical dictionary, reading words back and forth until we landed on Helm. And that was where we came up with the name Helm, and charts and all of that was sitting there with a nautical dictionary, neither of us knowing anything at all about boats or ships. But from that, Deis Labs got acquired by Microsoft, and they split our team into two. One team went off and built AKS, the Azure Kubernetes Service. And my team, they said, well, this Helm thing's really cool. Keep working on Helm and just start doing projects for CNCF. Build new, interesting open source tools, push them out into the open, go to customers, go to other people inside of Azure, learn what their problems are, and try and solve them in open source. It was the most awesome job anybody could have at Microsoft. So there were a team of about 14 of us. We built all kinds of things ranging from I think some of our earlier ones were Brigade and Draft, and we moved on into OAM and CNAB and a whole bunch of different projects that all kind of came out of that one little team in Microsoft. It was a lot of fun. Along the way, anytime you're doing that kind of open-ended R&D work, you start to hit intractable problems, things that customers or internal Azure teams were telling us were problems, and we'd try and solve them, and we couldn't figure out necessarily how to solve them with the existing technologies. And so we dove into some of these, and that's where the story that I'm going to tell today about WebAssembly on Kubernetes, that's where this story comes from. It was something that came out of several different interesting conversations we had with big Microsoft customers, with Microsoft core teams themselves. So there are kind of two big points that I hope when you walk out, you remember these two. This is one, and the other one, keep an ear open for it, will be the component model later on in the presentation. But this is how we're parsing out the world at the time, right? So pre-cloud, in the pre-cloud world, we had a bare metal machine, and it had a single instance of an operating system on it. So there was this one-to-one relationship between your hardware and your operating system. And this gets reflected in a lot of our language, right? We talk about server, and sometimes we mean server as the operating system instance, and other times we mean server as the piece of hardware. That's because we all sort of assumed that there was this one-to-one relationship between the two. Now, when virtual machines came around, that equation changed a little bit. And an upstart online bookstore figured out that they could sell their spare compute capacity and turn it into kind of a secondary line of business. It's now probably their main line of business, right? So AWS really kind of defined for us this idea that we could build a cloud where we leased somebody else's hardware, ran our instance of an operating system on it from kernel and drivers all the way to our application code. Now, virtual machines are powerful, right? They're going to be around probably till the heat death of the universe as a concept because we get so much done. Most of Azure services, Amazon services are all hosted on virtual machine instances. But when it came to the developer story behind building virtual machines, it was painful. I remember trying to, as a small development team at a startup, build a system where we were building and maintaining our own virtual machine just to run a single microservice. And suddenly, my 3-person developer team was responsible for everything from kernel-level vulnerabilities up to making sure our application code was running, and that was just too much for a small team to take on. So when we first got a taste of Docker containers, we're going, oh, this is great. Instead of needing the whole operating system from kernel and drivers up to the top, you get kind of a pie-shaped wedge of an operating system, right? Just the libraries I need, just the chunk of the file system I need, and then just my service on top of it. So if you're thinking of virtual machines as sort of like the heavyweight class of cloud computing, right, the big burly battleship, then containers really come in as sort of the middleweight class. And they're very, very good for running long-running processes. Processes are going to run for hours or days or months or even like quarters or something like that. And containers are just fantastic for that. So here we are in Azure, and I get to a meeting a little bit early. And one of the other guys at the table is on the core Azure compute team. And we're killing time. And I look at him and said, so, what would you say is like the biggest challenge for Azure compute? And I was like buckled in for the super arcane, like, well, when it comes to power management and the way we have to do this across multiple data centers or something like that. He looks at me and says, our core problem is really easy. We rack servers as fast as we can. And they get consumed as fast as we can rack them. But most of them are sitting there averaging 80% or more idle. And the thought of how much computing power was available and how much of it was actually just idle was like instantly sort of mind-boggling to me. And the first thing I thought was, well, that can't be right. And the second thing was, if that's right, we got to figure out something to do about this. So I started looking into it. Our team started looking into it and finding out what was causing idleness. Some of it was Kubernetes workloads where you scale out to 5 because you need to be able to handle peak traffic. But most of the time, you're not at peak traffic. You're at average or below average traffic, right? And the other workload we found that was particularly wasteful was Azure Function as a Service architecture. And when we looked into how this worked elsewhere, we discovered it was actually the same problem elsewhere. Virtual machines take a while to start up. At the time, they took between 30 seconds and a couple of minutes to start up. It's a cold start. You can't send a request, wait for 30 seconds to get the machine started up, do the response, send a response back, and expect to have happy customers. So how did they get around it? Well, they queued up a massive queue of pre-running virtual machines. And a request comes in, and it pops the first one off the queue, drops the application code on it, executes it, tears the whole thing down, and plops another one on the back of the queue. We knew from our research that developers loved writing serverless functions because they were nice and easy to build. But when we learned how wasteful the infrastructure was, we went, that's an area where we could solve some problems. So there were a couple areas like that we started saying, okay, so what are we looking for? We're looking for a third kind of cloud compute. One that'll sit side by side with virtual machines and containers, but will be optimized for fast cold start times, the ability to spin up, spin down, allocate memory very safely, and we had kind of a pretty good idea of what the shape of the technology was going to be. And we went, okay, let's go find a layer of compute that we can insert in here alongside virtual machines and containers. And as you can see, because I put it up here, WebAssembly was the technology we ended up discovering. And we'll come back to that in just a minute. But before that, I wanted to show you why we got a lot of enthusiasm about serverless development and what we mean by serverless in this case, right? So this is a complete serverless application that does Hello World in Spin, which is our WebAssembly serverless framework. So it's about 6 lines of code. All it does is expose a particular function that gets called, handed a request, creates a response, and returns it. There you can see that's line 1. There are no imports or anything hidden above it. That's really the entirety of it. So we can see very clearly here what server we're doing without, right? There is no software server here. We're not starting up a server that's listening on a port for a long period of time. Instead, a request will come in, it'll execute this function, run it to completion, return a response, and shut back down. So what we're doing without is that long-running process that's sitting there consuming resources all of the time, and instead allocating as fast as we possibly can just the resources we need to handle this function, return a response, and then shut it back down and clean it back up. That becomes really important because you can achieve very high levels of density and consequently get rid of that 80% idle thing if you can really load these functions onto a particular server and then they get interleaved and you can end up achieving very high levels of density, 2,000-3,000 applications per AWS 2XL image, right? So orders of magnitude higher than what you can usually get with containers. So why WebAssembly, right? So many of you probably, when you hear WebAssembly, immediately go the route I did the first time we threw this idea out here. That's a browser technology. It was built for a very specific purpose, which was to run code other than JavaScript inside of your web browser. There was a story that I thought when I was at Microsoft was a fable, but turns out it is true. When the Microsoft Office team was porting to Office 365 at the time, they were working on Excel, and there was a C library that had been around since the mid-1980s, and nobody knew what it did. But they knew that it needed to work exactly the same way for Office to work online. So somebody would have had the ignoble job of translating that very dense C code into a JavaScript implementation of the same thing. But then they said, well, wait, we could just use WebAssembly, compile the C code to a WebAssembly binary, and call into it from the outside JavaScript in the browser. And that's exactly what they did to great success. So one of the design intentions of WebAssembly was to make it possible to bring older libraries and older code into the browser and run it in browser. Another one was to be able to really lean into the strengths of a particular language. So when Figma wrote their high-performance vector math implementation to run in the browser, they wrote it in C++, compiled it to WebAssembly, and call into it from JavaScript. So those were kind of the core use cases for the browser version of it. But if you're going to run in the browser, you have to check off a few table stakes kind of checkboxes. Number one, it has to be secure, because nobody wants their browser to get rooted by some 1985 C library that nobody knows what it does, right? And so the security sandbox for WebAssembly actually had to be stringent enough that not only did it protect the browser and the underlying operating system, but it also protected the JavaScript that was calling into it, so that you couldn't even use the WebAssembly as a vector to attack people's JavaScript. So that was the original design of the security sandbox. Second piece, if you're building for the browser, you got to be able to run on anything. You can't say this page is not available on macOS or this page cannot run on ARM. And so they needed a binary format that was both cross-architecture and cross-operating system. And that's well beyond. Sometimes we talk about like Docker as being cross-operating because it runs on Windows and it runs on Linux. But this has to actually run on anything from our daily desktops down to the embedded operating system that's running on somebody's fridge, right? So WebAssembly was built with the cross-platform and cross-architecture, but it was also built for a fast startup time because nobody wants to wait for anything, right? And we are very impatient when it comes to waiting for sites to load on the internet, right? In fact, a lot of research suggests that the time window is somewhere between 10 milliseconds and 100 milliseconds before somebody's attention begins to dwindle. Google actually starts to ding you when you cross 100 milliseconds before time to first byte on the page ranking. So this is kind of a well-known thing in front-end development, kind of a surprise to me as a back-end developer. But so WebAssembly was built to be very, very fast to start up and very, very fast, near native as possible to execute. So it has JIT and AOT and varieties so that it can speed up execution. And then finally, and this is actually by far the most ambitious thing that the WebAssembly group tried to do. So WebAssembly was started by a team at Mozilla who then, roped in the Safari team at Apple, the Chrome team at Google, and at the time, the IE and Edge team at Microsoft, which is now another Chrome team, and said, let's work on this together. Let's work on this as a standard within W3 alongside HTML and CSS. And we'll build this system that should be open enough, right? And if you think of all the other attempts to add other languages to the browser, Flash, Silverlight, Java, they were all proprietary. So their goal here was, let's make it open enough that anybody can work with it. And let's make it general enough that any language should be able to execute in this environment. So anything from C and C++, which we already talked about, to the bytecode languages like Java and .NET, on to scripting languages like Python, Ruby, and even JavaScript itself, should be able to execute inside a JavaScript, inside of a WebAssembly runtime. By far, That's the most ambitious thing the WebAssembly team tried to do not because of the technical nuance, actually because of the social problem of getting all of these different language communities aligned on your specification and doing it. So I've been tracking over the years how many languages are moving over to WebAssembly. RedMonk puts together a top 25 list. Almost all of the languages in the top 25 are in some stage of migrating over to WebAssembly as a compile target or as a runtime target. The outliers right now are Objective-C, which in theory should be able to run, but nobody seems to have tried it because everybody's using Swift, which does work, and Java. The Java community has been the only one that's sort of resisted on philosophical grounds that they can already do that. But all the rest of them are moving. .NET 9 comes out with WebAssembly support. I think the beta drops within the next couple of weeks. So one of the biggest, most established enterprise languages has moved along with C, Go, Rust, Python, Ruby, and even PHP. But, and one thing I should point out here, though, is, so here's the checklist of things that were necessary for the browser. This happened to be a big chunk of the checklist that we were looking for as we were looking for some kind of server environment. Because what we wanted was every cloud compute engine has to be run in a secure, sandboxed way. We really wanted it to be able to run on ARM, on Intel, on Windows, on Linux, because ideally you should be able to make use of the cheapest available compute hardware without having to send things back to your developer team to redo their code. And so we're going through this checklist and going, this lines up really well with what WebAssembly was already doing. All we need to do is take the WebAssembly runtime, pluck it out of the browser, drop it in on the server side, and build a cloud environment for us. Turns out we were not the only people doing that. The Bytecode Alliance, which is actually an organization working on the specifications and reference implementations, had just gotten started. We began participating in that, first as Microsoft, now as Fermyon. And they're building a set of specifications that make it possible to link to a system interface instead of linking to a browser interface. So the WebAssembly system interface, WASI, is the description of how you run WebAssembly inside of a system and what capabilities get exposed there. So to that end, we started a company called Fermyon and began building the set of tools that we believed were necessary to realize this kind of third wave of cloud computing. First tool we built was called Spin. The original author is sitting in the very back row of this room right now, so you can all turn around and embarrass Radu, who's back there. And Radu said, we need a developer tool. What did Docker do to get successful? They built a tool that developers loved and infrastructure teams appreciated the value of, and instantly, where you're usually fighting wars over who gets to decide what technology, you've got two teams agreeing on what you want to do. So we built Spin following that same kind of pattern. It's a tool that was our core user story. The entire first year we worked on it was, as a user, I should be able to go from blinking cursor to a deployed application in 2 minutes or less. That was our success criteria. And the goal there was to say this should be really great for developers. They should fall in love with this tool because it's easy. It has a couple of commands. Spin new scaffolds out a new project. Spin build builds your project using whatever tool chain you need. So if you create a Rust project, it'll drop down to Cargo. If you create a JavaScript project, it'll use NPM and so on. And then you can run Spin up to test it locally and Spin deploy to push it out to a hosted provider. We'll talk about one of those in a moment. We recently added Spin Test, which also adds the ability to test all the interfaces to make sure that your application abides by its design constraints and can run its unit tests. So now let's go back and real quick. So we looked at this 6-line function here, right? This is a Spin application written in JavaScript. You can kind of see in the tree over here, we got one JavaScript file. We got the package.json files that are typical for any node-based application. There's one spin.toml file that tells it how to map an inbound request to the function. Very straightforward file there. And that's about it. It's about all there is to a Spin application. So again, the design was to go from blinking cursor to deployed application in 2 minutes. That means we had to have very few things that the developer needed to look at and understand. I one time decided I would test this against AWS Lambda, because Lambda is, of course, the venerable original serverless framework. So I created an Amazon account and created and downloaded Spin. And I timed myself going from the beginning of the Hello World documentation on Lambda to having it deployed and routable to my application, and then did the same thing with Spin. Spin lived up to the 2 minutes thing, but it took me 40 minutes, even though I'm relatively well versed in cloud technologies, to be able to get my Lambda function running. And I thought, okay, this is encouraging, because if Lambda can succeed at that level, with the developer experience, it's that difficult. If we can streamline the developer experience, we'll make even more developers happy and comfortable in that kind of environment. So, third wave of cloud computing, virtual machines, containers, and WebAssembly. Where do we run our WebAssembly? Well, you should be able to run it on bare metal. You should be able to run it on a variety of things like that. We use Nomad as our orchestrator inside of Fermyon Cloud. But the main one we were really interested in is how do we run WebAssembly inside of Kubernetes? And we took a couple of different shots, one actually even before Spin, and tried running it using a virtual kubelet style. It worked. Crustlet, the project, made it into CNCF. We worked on it for a couple of years and then started to see that actually that was not going to give us the kind of experience we wanted. And we started sort of recategorizing how you run things in Kubernetes. You know, you can run something on top of Kubernetes where you just deploy workloads into it. You can sort of fake it, which is what virtual kubelet does, and pretend and deploy kubelets, kubelet-like things that act like kubelets, but are their own little beast. And the problem with that one ended up being that all of the things that we implemented there were detached from the rest of the Kubernetes system, like the volume system, the environment variable system, and we found ourselves basically replumbing in all of the architecture for Kubernetes. Well, that's sort of a non-starter. That's really not what we set out to do, was build a highly complicated middle layer inside of Kubernetes. So the third way was to say, well, what if we just run it? What if we just go down to the level of the container runtime, containerd, and when a pod gets deployed and the pod definition gets piped all the way down to containerd, say, oh, well, if this is a WebAssembly binary, don't run it with a container runtime. Run it with a WebAssembly runtime. Now, the advantage of this is that for all of the rest of the Kubernetes, your WebAssembly binary looks exactly like a container. And for all practical purposes, basically performs exactly as a container. And so you can use volume mounts, you can use secrets and config maps and service meshes and all of that kind of thing. But in actuality, instead of running these long-running server processes, you're just running serverless functions that are handling requests when they come in. And so by doing this, we discovered that we could actually achieve a much higher level of performance inside of Kubernetes. So typically, research suggests that even on very large installations of Kubernetes, the average Kubernetes node, and it didn't say what size this node was, but the average Kubernetes node actually only can run about 30 containers. The limit's 250, 30 is what we could hit. With WebAssembly, we could easily hit the 250 limit without breaking a sweat. And if we worked around the networking stack in Kubernetes, we actually managed to get it up to about 3,000 applications on a 2XL Amazon node. So we could just, orders of magnitude, again, more dense than what we could achieve there. What kinds of use cases does that fit? Well, so again, because you're allocating and deallocating everything, each request coming in, right? So startup, handle the request, respond back. You can run lots of applications and have them interleaved. So if you have a lot of different microservices, and it doesn't have to be 3,000 before you start realizing the benefits, right? It's really at around a couple dozen you start to realize the benefits of this kind of rapid startup, handle a request, shut down. So suddenly you can handle a lot more requests across a number of different applications. So if you have a lot of different microservices, this works really well. Another case is if you have very bursty traffic where things need to go scale from 0 up to tens or hundreds of thousands very quickly, this system works very well because it's so parsimonious with resources that you can scale up and scale down as fast as the requests come in and then as fast as they drop off. And then a third case is sort of like if you have cases where traffic is unpredictable and bursty, like say a big order pipeline. And if you go watch our Zeiss talk from KubeCon Paris, we talked about this case where they would get 10,000 orders, need to process them in seconds, and then clear the whole queue because if the queue got backed up, bad things happen. Those are the kind of use cases that WebAssembly inside of Kubernetes really shines with. But you can also do some very interesting things, like if you're running a lot of sidecar pods that are just eating up a lot of memory, because we can run side by side, you can actually start replacing sidecar containers with sidecar WebAssembly modules, which will only spin up when a request comes into the sidecar. So if you're doing something more Dapper-esque, where you might have a service that needs to handle a call once every few dozen requests, you can drastically cut down the amount of space that you need, of disk space, memory and of CPU. So we released, along with Microsoft, SUSE, Liquid Reply, and others, we released SpinCube at KubeCon this year. So SpinCube makes it possible to run Spin applications inside of Kubernetes. So there's a nice little diagram there, but if you want to read more on that, and I'm running out of time, spincube.dev will give you sort of the overview story of how this all works. So that was all telling you a story about what made WebAssembly interesting for solving a current problem. But there was one more thing that we had in mind even from the beginning. Kubernetes was sort of a stepping stone along the way to true distributed computing. It used to be the case when I was in college, distributed computing was like the last course you got to take, like 400 level something or other, because it was so complicated and people were doing all their PhD work on it, but nobody had an off-the-shelf sort of distributed computing platform. Kubernetes comes along and the microservice design pattern comes along, and suddenly we're just writing distributed applications. That's what we do, right? But it should be even easier than it is. Right now, it's incumbent on the developer teams to build up microservices themselves. They pick apart the different services. They say this one's going to do X, this one's going to do Y, this one's going to do Z. And then you kind of end up with this case where you're always marshalling into JSON and sending it across the wire to another service. And you start introducing both developer inefficiencies in that they have to maintain all of this distributed code, and network and system inefficiencies in that you have to manage all the routing. So WebAssembly's got this thing that we've been working on for a few years. It's just finally now coming to fruition. February was when the standards group voted on it. And it's called, very boringly, the WebAssembly component model. But essentially what it does is it allows you to take two WebAssembly binaries and say this binary can use this interface to talk to this binary. These are the functions it can call. These are the objects that it can pass back and forth. And when you do that, suddenly you open up a very new world of the kinds of things you can build, because you're compiling all these different languages to the same binary format, and you're describing how one binary can call into the other binary. And all of these things are platform neutral, very fast to start up and move around. And so suddenly you can begin glomming together a whole bunch of different libraries as part of the developer process, which feels exactly like the usual developer process where you import a thing and you call the functions. So the developer is getting this experience where they're building things the way they always have. But what you get as output is a collection of components. And those components don't necessarily all have to run in the same place. It's really up to the WebAssembly runtime how it's going to manage all of that. So you've unlocked a couple of different things with the component model. The first one is you've unlocked this model in which the developer sits in their comfort zone and is building distributed applications. The second one is you've actually created a really good polyglot programming environment. You can take a library written in Rust, a library written in Python, compile them both to WebAssembly, and call in and out of each of those with your JavaScript code or with your .NET code, right? So we've unlocked polyglot programming, which is really the kind of the first time I think this has been done well ever. And the third one is if you're running each one in its own little security sandbox, you can start making security assertions not at the application level, but at the component level, and say, hey, this component that I downloaded off the internet that's supposed to just parse YAML, it's not allowed to access the network or environment variables or anything other than what I pass into it. This thing here that my developer team built, they need file system access, we grant them that. This thing has PII information, none of that data ever goes out of the module, and you can start laying on security parameters at that particular layer. Now there's no tooling yet for this, but the designs are coming along. And this, I think, is going to change the way that we can make guarantees about the security of our application. And I'm not going to say anything else about that because you're sitting in the audience and you'll know if I'm you're probably already hacking this in your mind. If you didn't see the previous talk, we walked through GitHub Actions hacks earlier, and it was, I'm going to go back and reconfigure every Git repo I ever own. But the component model is the other thing that I'm really excited about. So we've got kind of this 3 waves of cloud computing with virtual machines and containers, and now this ultra-fast serverless-style runtime with WebAssembly, and then this component model that allows us to start to build sort of a next generation of distributed applications. There's a QR code that will get you started with Spin if you'd like to take Spin for a spin. And also, we've got a Discord that's a great place to go and just ask questions. All of our developers hang out there. A huge number of the community hangs out there. And it's a great place to find out more. With that, thank you all very much. Appreciate it. Oh, I do have time for question, I think. So a couple minutes. We go for questions for a couple of minutes and then take 5 minutes between. Is that?
10 minutes right now between this and his session. So.
Okay, I'll do a couple questions and then we'll end it, and plenty of time for Phil to get all set up. Yeah.
So the component model, you would be able to do that in SpinCube as well.
Yes.
Okay.
Yeah, and in fact, the component model is built as part of the WebAssembly specification of the WASI specification, the system interface style, which means that VS Code introduced the ability to run components natively inside of their extension mechanism last week. And F5 introduced the ability to run components inside of Nginx Unit a couple of months ago. And so it is quickly becoming the kind of thing that will be standardized. And that's really good, right? Because why is NPM successful? Because lots and lots of people can use it. You know, why is Cargo and Crates successful? Because lots and lots of people can use it. So what we want isn't necessarily only Spin being the application environment this can run in, but as many of the WebAssembly environments as possible. Ideally, you know, browser, server, plugin, things like the VS Code extension model, all of those would be great places to run components. Any other questions? All right, thank you again. Phil? Oh, sorry, yeah.
Sorry, you beat me to it. Well, it's probably a naive one, but what's the difference between, I guess, what's being done here and like the Cloudflare isolates type?
So that is a great question. So isolates from Cloudflare is a way to run JavaScript within a VM, within a V8 instance. Cloudflare has largely, until very recently, been JavaScript only on that side. You know, I wouldn't be the person to be able to explain the details of Cloudflare's security model to you. The WebAssembly security model is kind of built on a different premise than Cloudflare's. But execution style, you get sort of this similar goal in that you should be able to execute a serverless function as quickly as possible and free up resources. But the implementation with WebAssembly is to say we're going to give you strong isolation into this bytecode format that'll be able to run any language. Again, the component model is different. But I would say of all the other serverless implementations that I've ever seen, Cloudflare's workers are the other one that I think is remarkably fast and resilient. So you can think about those two as being in you know, sort of the abstract-y way in competition with each other. Again, the nice thing about WebAssembly is by default you can run anything from C to Python and Rust and everything but Java inside of the runtime. And I dismiss Java, but actually there are a number of community efforts to get WebAssembly Java support. So it too is coming along. It's just coming along at a slower pace and without necessarily Oracle's endorsement at this point. Any others? All right, thank you all very much.